Introduction. So today, okay, yeah. Oh, I have to do something. I got it. Okay. So today we're very happy to have David to give us um, a talk on the factorial homology. So we're very glad to have him here because he's one of the co-founder of the subject. Especially, he developed this so-called beta version of factorization homology, which is slightly different, well, not slightly, quite different from the alpha version. We believe that the theory they developed is highly deeply related to what the physicists had in mind and what the physics really need. So we're really happy to have him to give us this talk, introductory talk on factorization homology. Yeah, David, it's all yours.
Okay, thank you for that introduction. Thank you for this invitation. Um, so I'll talk about factorization homology. Um, I'll be upfront that I made some guesses for how to speak to this particular audience. And please, as I go, at any time, ask questions, and I have plenty more to say, I'm sure, in response to those questions. I especially welcome that so that the talk is engaging to more folks. Yeah, also, before I say too much more, I'm eager to better understand just how to prepare this theory for applications in physics. And and so if any of you today have any comments along those lines, I especially welcome that. So most of this work is joint with John Francis, my ongoing collaborator, and other aspects are also joint with two other collaborators, Nick Rosenblum, who's an expert in derived algebraic geometry and deformation theory, and Aaron Mazelji, who in a sense was an early student of mine. Okay, so factorization homology. So what it is a construction. Here's the input. There's two types of input. One is a manifold. And that manifold, typically, I think of it as n-dimensional, but it's interesting and worthwhile to entertain cases where the manifold has dimension less than n. Additionally, for much of the theory, there's what's called a framing, and we can go into that if appropriate, but I'll mostly ignore that particular bit of structure. Depending on where we go to in this talk today, when I outline a definition of factorization homology, it will be clear how the framing is used here. But I think that that framing structure could be relieved with some more thought. Intuitively, in physics, I encourage you to think of this as a domain of a QFT, or possibly the bulk of a QFT or of a TQFT that's acting on a QFT. And we might go into that. So that's one ingredient for the input. Another, and I'm aware that this is a lot of technical words, and so I intend to elaborate on it a little bit more. The other input is I'll highlight as we go the main bit of structure. The other input is an infinity n category. Now, the number of mathematicians who are experts in homotopy theory that have a working practice with infinity n categories is very small. So I'm going to outline what I mean by this and how to produce examples of such below. Now, an additional condition on them is that they be what's called rigid. And think of that as a type of finiteness condition. And we also choose an object that we usually think of as the unit inside of it. Okay. There's more words here. Enriched over V. And here are some cases for what that V is. V could be complex vector spaces, or it could be chain complexes over C, or it could be sets, or it could be spaces. And I considered, and I always consider just writing a talk and even a paper where I just fix one of these choices once and for all. But there's advantage to having a multitude of options there for some of the examples that I'll bring up in just a little bit. Okay,
may I ask why you put the pointed there?
Yeah, so I'll say now, and I hope to come back to this a little later when we talk about the definition. The point will enable us to evaluate on non-compact manifolds. It's kind of like the point at infinity. So this has everything to do with these being possibly not compact. If you want a theory for only compact manifolds, you could not ever mention the point. Okay, so it's a really small piece of structure, but we'll see how it comes up in just a little bit. Now, intuitively, whatever on Earth this mathematical structure is, and the data of it is an n category that's enriched in, say, vector spaces, and that's a condition of it. It organizes the topological point operators, and how they interact themselves with the topological line operators, and how those interact with the topological surface operators, etc. So this mathematical structure is intended to capture, inspired by physics, all of the topological operators of all possible dimensions and codimensions, and furthermore, how they interact with each other. It's just remarkable that this pre-existing mathematical structure, an n category, has very much to do with these topological operators in a physical theory. Okay, so that's the input to factorization homology. It's a manifold, and it's an n category. And you can think of the manifold again as a domain of a QFT, and this n category as somehow organizing the point and line, etc., topological operators. Okay, so what's the output of this construction? The output is an object in V. So the best case to take, as I'll mention in a second, is where V is chain complexes, in which case factorization homology will be a chain complex. And a way to think about it is all possible observables or operators, at least those that are topological. It organizes all of them. So that's what this talk is about. It's about this construction. And I'll just make a comment in real time here, is there's a lot of shadows of this construction. The more I read other people's works that have to do with mathematics of theoretical physics, the more shadows of this I've seen. And if I were to identify what the new aspect of this theory is, it's really that it's derived. And I'll elaborate what I mean by that, but it is a construction that makes no choices, such as it does not make a choice of a triangulation of M in order to define this, and then later have to show that that this construction was independent of that choice. So I'll just note this, that the advantage here, the key novelty, is that this construction is manifestly well-defined. So no choice, no triangulation, etc. And it's also derived. And I'll speak to the advantages of derived in just a moment. Okay, so that's factorization homology. As I mentioned, typically the enrichment is in chain complexes, and I invite you to just think of that example from here on out. And typically, one is interested in the zeroth homology of this chain complex, which will be a vector space. So as we will see in just a bit, if one is only interested in the zeroth homology of a chain complex, there's still advantage in remembering that chain complex, such as for otherwise unforeseen local to global expressions, such as Meyer-Vittora sequence, and also such as discovering ghost symmetries. And I'll bring up both of those 2 points in just a little bit. Okay. Are there any questions at this stage?
Hi, I have 2 questions.
Please.
First one is if it's enriched in chain complex is a DJ category, and there is another notion of the rigid DJ category in the book of Gansky and Rosenblum. Is any relation with that notion rigid of and this rigid?
Yes, they coincide when they're comparable. So thank you for that question. And I'll just sneak that in real time, a remark. When n is equal to 1, then some of you might have already known this definition. Well, okay, I'm gonna say n is equal to 2 actually, and for r, actually let's say a rigid DG category, and there what this means is that there's a monoidal structure, and with respect to that monoidal structure, every object has a left and right dual. Then you can take its D loop. So this will be a 2 category, I'm going to talk about this in a second. This will be a 2 category that's rigid. Infinity 2 category. And it'll also come with a point. So that's a great source of examples in dimension 2. So Gansky, Rosenblum in dimension 2 for rigid DG categories, that produces examples for n to be 2. So a theory for us for surfaces. Thanks for that. Any other comments or questions out there?
And this point is the monoidal unit or anything? I see.
Yeah, exactly. That's why I like this notation, because it looks like the unit, because in practice it will be the unit. Okay. Here's a informal definition of an infinity n category. So you are welcome to just omit this if you like, just for discussion's sake. Though, as I indicated above, the real advantage of this theory is that this is all true in a derived setting. And so how the most fantastic examples arise is by not omitting the infinity. But you're still welcome to get the spirit of what this is. So an infinity n category, or just think n category, it consists of a moduli space of objects. And here's an example. If, and I should have said this is an example when n is equal to 1. In that case, you can take consider the ordinary category of vector spaces, finite dimensional, and the set of objects is the set of finite dimensional vector spaces. And what I mean by the moduli space of objects is, well, the moduli space of finite dimensional complex vector spaces. And one way of describing it is as this coproduct of BGLN of C's. So an infinity n category consists of a moduli space. Think of it as the maximal subgroupoid of a given example, such as here. And then for every pair of objects, there's a moduli space of 1 morphisms. And for every pair of 1 morphisms, there's a moduli space of 2 morphisms, etc. And at the very top, for given 2 n-1 morphisms, there's not a moduli space of n morphisms, but a chain complex of n morphisms. So this is where we see the enrichment. And together with some composition rules. So if you fix a k between 0 and n, there's a composition rule like this. And in fact, there's, in a sense, k-1 types of composition rules for k-morphisms. I hope to draw some pictures in a bit to indicate that have to do with the surface operators, etc. Let's see, I just got a prompt. I'll broadcast. Can you still see my screen?
Yeah.
Yeah.
Is it moving? No.
No, it's not moving.
I need to restart Zoom. My apologies.
Oh,
it's cut out.
It's okay. Okay.
Okay, sorry about that. I don't know why that happened. Okay. Can you see the screen and is it moving now? Okay, great.
Yeah.
Okay. Intuitively, the n morphisms that and the way I'm drawing pictures, n will be 2. The n morphisms are the topological point operators in the theory. So here's a surface, and given 2 points, you can think of them as sites for inserting a point operator. And actually, this way of talking about the n-morphisms is only valid if they're n endomorphisms of that special point that we chose. So think of the unit. N-1 morphisms you can think of as topological line operators, etc. Let me draw a couple more pictures. So here's a more complicated network on a surface, and one can think. So if let's call this alpha x y z. What's happening in this site here is locally, it looks like this picture. Which I can interpret as a morphism from, if I read you can see where framing is used on the manifold. So moving upward, I see y first and then x. So this is like x tensor y alpha to z. Is that that kind of structure? So what I'm indicating here is intuitively how to think of an n category in terms of topological operators on it, on a manifold.
So you're suggesting that this framing tell you the order of the tensor product.
That's right.
But what if you have a xy lying horizontally in the first direction, not in the vertical direction, but in the,
yeah, good.
Then you have a, you want to use the second tensor product.
Right. So in a sense, we could. So this picture is kind of isotopic to this one.
Mm-hmm.
Oops. Which is in turn isotopic to this picture. So these string diagrams may look entirely familiar.
Mm-hmm.
And I can just relabel this by not y, but y with its, I'll just call it y dual. And that I can interpret as a morphism from x to z tensor y dual.
Okay.
So good thing we're in a rigid category. Rigidness was a condition that I didn't say for that definition up there. So that this kind of maneuver is allowable. So we still use the framing, but what we're in a sense observing is that, well, anyway, so it was what this comment, I hope it's illustrating, is that we're still using the framing, though these kind of interpretations, as alluded to here, are invariant with respect to isotopy. Yeah. So all told, we should, however we're interpreting these pictures, it should be such that these two data are the same, and in a monoidal category in which every object has a dual, they indeed are the same data. Okay, so what I had in mind is that that would be as much as I'll say for the time being about the definition of an N category. Certainly, I'm happy to go into a rigorous definition or just more intuitions as we like. Barring any comments, I'll move on. I thought I would say some examples and computations before I talk about features of factorization homology. So if right now you're feeling, or you're just wondering what are, well, I figured to get a sense of what factorization homology is, we can see some easy computations to start out with. So one, and I'm bringing this one up first because can you still see my screen?
Yes.
Okay.
But even it's the recording, it's okay. But it said recording failed to start. So from your screen. I think it's from his screen. It's
So
not
from our side, it seems okay.
Okay. For some reason, my feature of using the highlighter is not working, but that's okay. Okay, so why this theory has the word homology in it. One explanation of that is that homology is an instance of factorization homology. So I'll just mention that real quick. If you fix an abelian group A, you can construct a space, which is the Eilenberg-MacLane space for it. And there's a few standard notations for that. One is BNA, another is KAN. And a feature is that this is a pointed space with homotopy groups that are either 0 or A, and it's A in the named degree, and it's 0 in all others. And there's a standard way of regarding a space as an infinity n category in a very trivial way. The space of objects is BA, BNA, and the space of one morphisms is the path space, and the space of two morphisms are the space of maps from a two-dimensional disk into BNA, etc. So there's a natural way of regarding every space as an infinity n category, and it will always be rigid, it turns out. And because this space is pointed, then so will the associated infinity n category. Now, it turns out that factorization homology of it is a moduli space of A-labeled finite subsets of M. So here's a way of indicating what it is. A point in there is a finite subset of M, together with a map from that finite subset to A. And here's what a picture looks like. And I hope this is commensurate feeling with the picture I mentioned a moment ago of point observables. So in a sense, we're thinking of this abelian group as the point observables in this very trivial theory.
May I ask a question?
Yes.
My knowledge about this integral is that if you will be able to integrate over a manifold or even on an n disk, you probably should require the integrand to be in algebra in some sense. But what in this B and A, in what sense it is in algebra?
Yeah.
Or am I in a, or is you mean something totally different?
No, that's a great question. I was going to say a word about it in a moment, but I'd rather respond to the questions as they come. So here's some examples. Here's some examples of how to construct infinity n categories. So let let's say G be a group, then there's a construction BG, and that's an infinity one category. And it's in fact pointed. And what is it? The moduli space of objects? There's a few ways of saying this, and I'll say the most intuitive one is point. And the one morphisms in this category from point to point is equal to G, and the composition rule is equal to the multiplication rule of G. And this is pretty general. So more generally, let C be a monoidal one category. Then there's a way to regard it as a two category. BC, this is a infinity two category. And it will be pointed as well. And there's a few ways of describing what the moduli space of objects is, and one is just as point. And the one HOM in this construction from point to point is the moduli space of objects of C, and the two HOM from C to D is the one HOM in C from C to D. And you can see this is pointed as well. And it turns out, I name this as a fact, but it's an easy fact once one knows the definition of rigid, is that BC is rigid if and only if every object, oh, whoops, I forgot to say what the composition rule is. Composition is the tensor product in C, so that's where we use the monoidal structure.
Mm-hmm. Mm-hmm.
And, is rigid if and only if every object in C has a left and right dual. So that's a great way of producing examples of infinity two categories from monoidal one categories. And this is more general, even still, is let A be an EK algebra in infinity n minus k categories. In other words, it's a EK monoidal n minus k category.
Mm-hmm.
Then there's a similar construction. You can de-loop 3 times.
Mm-hmm. Mm-hmm.
And this will be an infinity n category, which is in fact pointed.
Mm-hmm.
And there's a similar fact, is that if A is rigid as a infinity n minus k category, and as a monoidal category, you can just look at the underlying one category. But then that's the same as BKA being rigid. And to finish this example, if this is an unfamiliar phrase, so my highlighter is dead for some reason. Oh, no, there we go. if EK monoidal category is an unfamiliar phrase, it might be more familiar by these two comments. An E1 monoidal, infinity one category, is the same thing as just a monoidal, infinity one category. And secondly, is that an E2 monoidal, infinity one category, and that in fact just one category, is the same thing as a braided monoidal, one category. So this might be a familiar notion, namely braided monoidal categories. And that turns out to be the same as an E2 monoidal category. So I'm giving context to this general notion of an EK monoidal category. And as an extreme case of this, if K equals N, we see that in particular for an EN algebra, then this D loop, the n-fold D loop, will be an example of a pointed infinity n category that's the condition of being rigid is vacuous, so it'll always be rigid. So if an EN algebra is a familiar thing, then that's great because you automatically have a large supply of examples of pointed n categories, namely those that arise from their n-fold D loop. And if I'm going to name one other fact, an EN algebra is the same thing as a Poisson, an n-shifted, or actually n-1 shifted Poisson algebra, which is a commutative algebra and a n-1 shifted Lie algebra. And for this to make sense, it's got to be in a DG setting, and then such that that the Lie algebra structure is a derivation with respect to the commutative algebra structure. So so Poisson algebras therefore give examples of infinity n categories that are rigid. Thanks for that comment. I was going to mention something along those lines in a bit, but that's great to have it now. Are there any questions before I move on to some computations and examples?
Can I ask a question?
Yeah, please.
Okay, just as you have just explained, given an EN algebra A, we can construct a pointed infinite n category, BNA,
Yeah.
right? So now, can we compare the results of, we can take factorization homology of A, and we can take factorization homology of BA. So the result is the same?
Yeah, perfect. So this is not definitional, it's a theorem. And it can be simply stated like this: A over M. And I'm going to tag this with an alpha version, as in like the first model of like, you know,
Yeah.
And that's equivalent with this beta version for BNA. That's right.
Okay, thank you. May I ask another question?
Yeah, please.
So given a pointed infinite n category, And I think we can construct an which is enriched in V, okay, where V is a symmetrical monoidal infinite category. And I think we can construct an EN algebra in V by taking the Hom category of this distinguished object iteratively.
Yeah.
So what is the result of the two factorization homologies? The first is we take. Okay, I think you can understand my question.
Yeah. Thank you. So let this be a pointed infinity n category enriched in V. Then one can extract from it the n endomorphisms of that point, and the composition rule will endow this. So this is a chain complex, or generally this is in some object in V, but the composition rules give this an n-1 sphere worth of composition rules, and really what I mean is this will have the structure of an EN algebra in V. So now one can, and furthermore, if there's a functor, which is, in fact, this is fully faithful with image, everything isomorphic to point to the unit. So this selects out that component. And as we will discuss, I hope in a moment, that induces a map on factorization homology. So I'm going to use the above fact, so the alpha version. To the beta version. And that is not an equivalence, generally.
Okay, I see. Thank you.
Yeah.
Could
well,
you?
can I? Oh, go ahead.
So this
is there any result telling us when is this guy an equivalence? This induced map. Yeah,
I really appreciate these questions because it's giving me feedback on what to focus on. So there's another theorem that, as I think I'll mention in a little bit, for M compact or closed and n-dimensional. Note that I said it can be evaluated on less than n-dimensional things. Then there's Morita invariants. That if R and R prime have the same categories of modules, then that implies factorization homology for them are the same. Now I bring this up because as an example, so if you fix, let's say that's an associative algebra, a ring, or DGA, then you can look at BNK, and that maps to perfect modules for K, as does endomorphisms of any perfect module. And both of these are Morita equivalences. And that means factorization homology of all of these things are indistinguishable. And I should have said this is non-zero of a K module. So if if R is not necessarily equal to the n endomorphisms of its unit, but if it's Morita equivalent to it, for instance, if so I'll say what it is. If perf, and so this is an n categorical version of perf. If perf of that En algebra is Morita equivalent with R, or for instance, if R is just equal to perf of it, then you get the same answer. That I hope that makes sense.
Okay, thank
so
you.
David,
yes,
so
please.
David, I still have some trouble to understand the beta version. I sort of know this alpha version. So the beta, so I'm guessing that the beta version is that you should consider M with a stratified manifold, some stratum, and you decorate it by some lower morphism of R. Is that what you mean?
Yeah.
But
Maybe,
however,
oh, go ahead.
However, if that is the case, then I'm even got more puzzled because the integral, in order to define the integral, you need to specify which stratum was decorated by which object in R, right? But if you just write integral like that, I wasn't able to tell which stratum is decorated by which object in R, or which k-morphism of R. How to see this integral beta version is well defined?
Yeah, I think I understand that question. So maybe I'll outline a definition of factorization homology now, and let me just comment that yeah, I'll do that right now. So here's a definition. The first part of the definition is it's the construction of a category. So what is this? This is a and it's naturally going to be an infinity one category. Though if infinity categories are unfamiliar to you, I encourage you to just pretend that infinity is not there. So what is this infinity category? An object is a disk stratification of M. And what's meant by this is quite specific. I'll draw some pictures because I think that captures the spirit. So let's say I'll draw some pictures when n is equal to 2. And imagine we're just looking at a patch of M. A disk stratification then is, well, it's a stratification of M by which looks something like this. And now you might know enough about a theory of stratifications to appreciate that without some regularity conditions, stratifications can be really wild. Like there could be, like we want to avoid infinite spirals and stuff like that. So a triangulation of M is just fine, is an example of such that has suitable regularity. And M is framed here. So I'm indicating a disk stratification right now. Notice that it consists of points, edges, and little polygonal surfaces. Those polygonal surfaces need not be triangles. They could be, but they need not be. So that's roughly what a picture of what an object in this category is. It's a stratification. What's a morphism? A morphism, or I'll say the morphisms, in M, in disk of M, are generated by, and I'm going to name a couple classes of morphisms, and every morphism will be a composition of these. So one type is just an isotopy of disk stratifications. So like you might see a local picture that looks like this. Oops. And it just kind of might move, but the combinatorics of the stratification remain unchanged. So I just wiggled these dots around a little bit. The combinatorics did not change of that disk stratification. Another type of move is an anti-collision. Of strata. So what that might look like is, if here's a piece of the stratification, we might see a movie where you see that horizontal line break up into two parallel lines. So if you read the movie backwards in time, you see these two lines, they collide to that one if you read backwards in time. So a forward morphism is an anti-collision. And the last type of move is a refinement. And by that I mean, oops. So this might look familiar from Fokker moves. So we just remove a stratum. So those are the morphisms in this category. I'll say as a remark, this does not look like it's a rigorous definition of anything. And one way to define this rigorously is to define this as a stack on stratified spaces, where you say that an S point of it is a stratification of M cross S, whose fibers over S are disk stratifications. Essentially, that's it. And we prove that given a stack on stratified spaces, one can construct an infinity category from it, which is essentially the exit path category of that stack. But anyway, so it captures this intuition. So I'm answering your question still. Okay. So this is a first step, is what is disk of M? So again, it's a whole infinity category in which an object is essentially a triangulation of M. Mm-hmm. That's a point in this category. Mm-hmm. And now next is that there's a fantastic functor frac C, and if you were wondering why the variance above, it was anyway. It's so that this this is contravariant to infinity n categories. And how is it given? Well, we're pretty much looking at the definition. You can imagine how this goes. Is what I mean. Given a polygon, so I'm looking at a little local picture of a distratification. You're staring at an n category, in this case, a 2 category. And here's where you use the framing. What is this 2 category? The dots will be the objects. The edges will be the arrows. And to know which way the arrows go, you make use of the first direction of the framing. You might be wondering if an edge was vertical with respect to the framing, what direction does that edge go? And this is all in some kind of infinity sense, and you just tilt the triangulation or distratification so that all the edges map isomorphically. They project to the first coordinate direction of the framing. And the 2 morphisms are in the second direction. So I'm given a distratification, which think triangulation. You can build an n category from it. So we use the letter C for like the category associated to a distratification. And making this well-defined is also its own enterprise, but in a sense, this intuitive way of discussing it makes it less obvious how to make this rigorous. There's a slick, so I'll make another remark kind of for the experts that really we construct a functor from theta n, which is known to be it's known to parameterize infinity n categories. We construct a functor from that into disks. And then what frac C is just a restricted Yoneda functor. So, yeah, and it reports the values as indicated here. Now, finally, the last part of the definition is, it's the colimit of this composite functor, disk of M. It forgets to infinity n categories, or it maps there by that map from point 2, just above, to the op. And then there's a functor to V, which assigns to infinity n category hom between infinity n categories from C to R. So that's why there's the opposite here. So all told, this sends a distratification D of M to the collection of functors. I'll denote it more informally like this. From the category you associate to D, so such as this picture, to R. Now, look, like in thinking about what such a functor is, well, it's an assignment of the objects to the objects in R.
I'm a little confused about this paragraph, the parenthesis D dot F M. What is what is that? This
That's
notation? I might forgot it.
Oh no, thank you. I said a disk stratification.
Oh, okay. This of M. Oh, I see. I see.
Uh,
Okay. This stratification of M. Okay.
yeah.
Then you got. I see.
Right. So this is essentially like such a thing here is
So,
an assignment of objects of this
right,
thing,
right.
which
So
are
it's
the,
right.
yeah, please go ahead.
So this functor C is basically give you a decoration of give you somehow a labeling of if I call the target category the category of the category infinity n category to be the category of certain defect of certain quantum field system. So the first C functor is basically give you a decoration of
Yeah,
all the stratum, right?
that's precisely what it is. That's right.
Then okay. Then what is R? R is
So
R is a coefficient system.
yeah, that's right. So think of it as like rep, you know, complex like of
Something.
or something like that. So in that case, this would select out for every dot. It would select out a G representation, and for every arrow, it would select out a linear G equivariant map, linear map.
Mm-hmm.
And that was a bad example for me to throw out there because it's a one category, not a two category. But
it's okay. So that's basically means that everything in that stratified picture, basically you wanna say the G acts on everywhere.
in for this example,
Yeah.
Yeah, so while you were talking, I upgraded it to make it the right dimension by taking the D loop.
Mm-hmm.
So there, let's decorate this. So each, so here's a bit of a disk stratification, and we label each of these by the unique object, which is point. So that's no data. We'd label each arrow by a object in this category, which is a G rep. So G acts on a vector space V.
Right.
G acts on another vector space W, etc. And then what this such a labeling such a functor here does to the two cell is it's the data of a map from the composite of these to the composite of those. And now because we're in a D loop, the composite of one morphisms is simply the tensor product. So this is a G equivariant map from the tensor product of U, W, V to the tensor product of A and B. So that's what this would be for that example of R, and for this particular disk piece of a disk stratification. So I heard you say a comment, and that was exactly right, which is that so this functor assigns to an object here, which is like a triangulation of M. It assigns to it the collection of the vector space of all ways of labeling that distratification by your input, your coefficient n category. And by labeling, I mean the dots by objects, the edges by morphisms, the two cells by two morphisms, etc., all compatibly.
Okay. Can I also go back to the three type of morphism you showed in the DSCAM?
Yes. Yeah.
There is an anti-collision, there is a refinement, isotopy of distratification. Well, that will maps to some kind of a isomorphism in the target. That's okay, I guess. But the anti-collision, what kind of a what was the image of an anti-collision of strata?
I was just commenting here that the isotopies that watch sticks rotate around.
Right. Okay, use the rigidity. Yeah. Okay. Yeah.
And now the anti-collisions correspond to just duplication to units. So if I happen to label this.
Oh, I see. Okay, I got you.
Yeah.
Yeah, the duplicates of units. That's fine. Okay.
Yeah.
I thought it needs some kind of a co-product. Oh, okay. No, okay.
Right. And then this has to do with composition. So if you're
given... refinement just doing composition. Yes. Yeah. Okay, no problem. Yeah. Okay.
Cool. Yeah, that's exactly right. These are great questions. I had in mind.
But anti-collision involves some choices, right? It depends on where you put identity morphism somewhere, but I thought you have some choices to make. For example, you can let the bottom one to be the identity, or you let the top one to be the identity, right?
Sorry. I think that question is generated by just some. So here, V is labeling the edge, and here V is also labeling that edge and that edge. And it's the two cell that's labeled.
I see. Oh, I see. Oh, I see.
Yeah.
Okay.
Thanks.
I see what you mean. Okay.
Yeah, and if that was even X and Y, this would remain X. That would remain X.
Okay. I see. Okay. Okay. I misunderstood. Okay.
Yep.
Thank you very much. Yeah.
Yeah. No, these are awesome questions. I appreciate it.
So I have another question. So this number 3, when M is a Riemann surface, it's going to be a Skein algebra?
Yes. So in general, it'll be a Skein category.
Yeah. Are you going to give this example from?
I had in mind talking about that. That's right.
Oh, okay. Thank you very much. I'll wait for it.
Well, it was going to be a quick pass. So maybe when I'll get to it in a moment, and if there's some specific questions you have that remain, we can talk about those. So I was
thank you.
Say a heuristic here in this co-limit. This is the vector space or chain complex. It's generated by. It has a huge generating set. It's generated by all labelings of disk stratifications of M, and then subject to relations given by the above morphisms / moves that we just talked about up here, those 3 types. And I don't mean literally quotient out by those relations, but do it in a homologically sensitive way. And again, that it is making this kind of construction rigorous that is really what the novelty is that we're bringing here is that it's this colimit in this land of infinity categories is so smart. It's implementing this intuitive idea perfectly. Okay. Well, I am appreciating these questions a great deal. I'll continue with what I had in mind, though. Please continue to speak up, and I can opt to skip some things based on interest. So, the first example I wanted to talk about was how factorization homology generalizes homology, and to see that one can take an abelian group, regard it as an EN algebra, de-loop it to regard it as an N category, and then take factorization homology of it. And that has a description as a moduli space of points labeled by elements in that abelian group. And I hope that this rings a bell to the informal discussion about topological point operators. And it turns out, it's a theorem of Dold-Kahn in algebraic topology, that the homotopic groups of this space are precisely the homology groups of the manifold with coefficients in A. So it's in that sense that factorization homology generalizes homology. So when the coefficients are that of the n-fold d-loop of an abelian group, it recovers homology. And there's a theorem that we prove which states that that factorization homology also computes the compactly supported mapping space. And you might know also from obstruction theory and algebraic topology that the homotopic groups of compact supported mapping spaces into an Eilenberg-MacLane space compute the reduced homology of the one-point compactification, reduced cohomology. So putting all this together, this computation here is implementing Poincare duality, an isomorphism between homology and cohomology. So I think there's two takeaways from this. One, from this example. One is that factorization homology generalizes homology, and the other is factorization homology tends to capture mapping spaces. And if these seem very different to you, and you're wondering what's the intuition for why these are the same, besides Poincare duality, choose a triangulation of M, and using that an Eilenberg-MacLane space is n-1 connected, you can choose a null homotopy of any such map restricted to the n-1 skeleton. In other words, a compact supported map from M to an Eilenberg-MacLane space up to homotopy is supported in a tiny neighborhood of the centers of the end cells of a triangulation. And that ultimately is what this looks like. Anyway, here's another computation, which is that the factorization homology over the circle is Hochschild homology. And maybe I'll just kind of leave this short, unless there are questions. I'll use it though to mention a structure. So given what I just said, factorization homology over the circle of the R equivariant, or the linear endomorphisms of a perfect R module, from what I just said, that's the Hochschild complex. And Hochschild complexes are Morita invariant. So that also so that means this factorization homology agrees with factorization homology simply over R. So this is a shadow of the Morita invariance I mentioned earlier, which is Morita invariance of Hochschild complex. And in terms of like point operators and stuff, you know, if somehow like the overall observables or state space is V, we can insert these point operators, which are endomorphisms of V, and we get a global observable as the trace of the composite of those endomorphisms.
So this can be understood as the S1 compactification quantum field theory.
Can you say that question again? Didn't quite follow.
So this can be understood as a S1 compactification of the QFT you consider.
It could be. Yeah.
Okay.
So here I was taking the theory was actually already just one-dimensional, and
Yeah.
and yeah, and then it would be a compactification just of that. Yeah, but there's,
Okay.
you know, of course, if you have a higher dimensional theory, you can take a compactification along a lesser dimensional manifold as well.
Yes.
That's right.
So
Yeah. So for one-dimensional
question.
theory, the S1 compactification is just the theory of Hochschild homology.
So a question. So the example you show so far, the integration is over in integration over this B, the delooping space. So in that sense, this beta version is the same as can be recovered from the alpha version, right?
Yep. Yep.
But are you gonna give us a non-trivial example that will go beyond the alpha version?
Yep. Yeah, I'll do that. And maybe I'll take this as an opportunity to mention that, so if one takes R, so this is n equals 1 still, if one takes R to be perf of a ring R, so this is a infinity 1 category, which is rigid, and it's pointed. Then one might think that you get a new value there as the beta factorization homology, let's say over the circle. That's the most interesting compact one manifold. However, by Morita invariance still, that's indistinguishable from R. So you don't get a new value, but it is a nice way to find even more symmetries. So I'll just mention there is a map from objects of R to here, but there's not an obvious map here. So the beta version of factorization homology, which for my own personal history in the context of algebraic K-theory and trace methods, I was interested in constructing such a map in a derived setting, and it seemed very hard. And so part of the reason that Nick Rosenblum and I even thought of or started thinking about beta factorization homology was in order to achieve this map, which is ultimately responsible for a trace map of K-theory, and then combine it with Morita invariance. So what I'm indicating here in this remark is that even though this value, which is an instance of beta factorization homology, is not new, it's the same as a previously known value, you get more features. Namely, there's a natural map from the moduli space of oops, I said of R, sorry, of perf. Every perfect module determines, therefore, a point in the Hochschild complex of R in a derived sense. So again, even though it's not a new value, you get more structure from the beta picture. Here's an example where truly the beta theory is necessary. This is, now that I'm looking at it, it's a little bit cluttered. So pick a semi-simple Lie algebra over the complex numbers, G. And, I invite you to just think little SL2 of C. And look at the finite dimensional representations of it. Well, actually not over it, but over the quantum group associated to it. So there's a natural deformation, of its, so one can look at the universal enveloping algebra, let's just say a little SL2, and that's the special value, the special value of a family of Hopf algebras that are all quasi-triangular, UQ SL2. So this is the quantum group. And one uses the semi-simplicity in a level to figure out what exactly this deformation of that Hopf algebra is. And what is meant here by rep Q of G is representations that are finite dimensional of that quasi-triangular Hopf algebra that are finite dimensional. A theorem of Drinfeld from, I think, 86 implies that this category of finite dimensional representations for this Hopf algebra is has the structure of being braided monoidal. And as you recall from an earlier discussion, that's synonymous with saying E2 monoidal. And that's the kind of thing that we can take the twofold D loop of. And the result is an example of a pointed infinity 3 category. Which because we're looking at finite dimensional representations, this infinity 3 category will be rigid. So the fact that every object in this monoidal category has both a left and a right dual is what's responsible for this infinity 3 category being rigid. So this theory of beta factorization homology reports a chain complex to this. And as someone was asking about earlier, that recovers the Skein module for the 3 manifold. So the statement in this, we hope to post shortly with Francis. And I say shortly, like in the next 2 months, which is that the zeroth homology of this chain complex is the Skein module of M.
How about higher homology group?
Yeah, well, so is your question to recognize the higher homology?
Yes.
Terms? Yeah, we don't know. Like, and not because so David Jordan, Sam Gunningham, Pavel Safronov, talking with them has been pretty fruitful. They seem to have an intuition for what the higher homology should be.
I see.
In particular,
it should be some floor homology, complex group Kroll homology, I guess.
I guess so as well. Yeah, and maybe you have some. I'm aware that some people have some intuition for why that should be so. And
yeah, I mean, physics tells us this, yeah, how homology should be flow. Yeah, I mean, this homology group should be isomorphic to flow homology M3.
Yeah,
I don't know. That's at least physics predicts.
I would be interested in picking up your intuition. When I've talked to some folks, the reason that should be the case doesn't seem to have anything to do with anything that resembles factorization homology to me, other than it's some complex whose zeroth homology agrees with Skein modules. You know?
Yeah, that should be flow homology of this B group
Yeah.
G.
Well, I'd love to talk about that.
Oh, okay.
Yeah, and I don't know if that's true, let alone why, but that seems to be what others in the community expect.
David, I have a more
Yeah.
elementary questions. This integral over M3, I wonder, you said this is go beyond the alpha version, but I wonder, I don't know when, where it really go beyond the alpha version. If you do not do the delooping, can you integrate the rep G, the Q, finite dimensional Q, directly over some kind of a two manifold,
Yeah.
or maybe a two manifold times R or something,
Right. So
to make it three-dimensional.
yeah. So maybe a first part of your question is that, so we still see a D loop here.
Yeah.
So why doesn't alpha cover this case as well? And note that this is a three manifold, and this is the twofold D loop.
Mm-hmm.
So this is just the next degree of in the beta direction. It's a E2 monoidal one category that we're integrating over a three manifold. It's not an E3 algebra.
Mm-hmm. Right.
And
Uh-huh.
yeah, so if you trace through the definition that I outlined of this, really this is a theory of decorated graphs in a manifold.
I see.
Yeah.
Uh-huh. Okay, that makes sense. Yeah. Yeah. I
Yeah.
noticed the difference, but I didn't realize that that's the key point. I see.
Yeah.
I have another question. So this rep QG finite dimensional, it not only braided, but also it's a modular tensor category, right?
Yeah. Mm-hmm.
This S and T modularness will play a role here.
Yeah. So in a couple ways. One is that I mentioned that this is for a framed three manifold, and it could in fact be taken to be oriented. That's a small point. As another paper that we posted about a year ago, every rigid braided monoidal one category has an action of the base loops of SO3. And that in fact is essentially trivial in this case. To see that, one can use the modular, that it's a modular tensor category. And for that reason, one can define this on oriented manifolds, not so it doesn't use the framing. But that's a superficial. So that's one comment, but it's a more superficial. A much more interesting feature of this.
Is that because it's a spherical? Because the trivialness is due to the sphericalness, spherical structure? Yeah.
That's right. Yeah, thanks. Yep. But so much more interesting about the modular tensor category aspect of this is that this theory can be defined on four manifolds. It can be extended to four manifolds.
Oh.
I don't have much to say. So essentially the center of this 3 category is sorry. This 3 category is dualizable over its center, and because it's a modular tensor category, and that's very interesting. And so we can interpret this as the state space of a 4-dimensional theory, and that's a bit outside of strictly as of factorization homology. More specifically, I don't expect factorization homology to capture that 4-dimensional theory.
I see. So this SL2Z, this SL2Z acts on this Skein module in that case?
Say that again, SL2C or SL2?
So yeah, SL2Z, this modular group acts on this Skein module, this H0 of this. Is it the consequence of the modular tensor category?
Right. I've thought a little bit about that, and I'll share my I'll say some words, and I just to be kind of generous, I don't know exactly what that structure has to do with factorization homology over a 3-manifold, but over a 2-manifold. So the framed diffeomorphisms of the 2 torus, it maps to the oriented diffeos of the 2 torus, which is SL2Z semi-direct product T2. So as a continuous group, that's what it is. And if you're and this turns out to be the braid group on 3 strands semi-direct product, the 2 torus. And there's a class, the braid group on 3 strands, B of it is the universal cover of B SL2.
Yes.
And this acts on the factorization homology of alpha story of rep Q SL of G, finite dimensional. And again, that feature of modularity, in particular, just that it's an oriented theory, extends that action, in particular, producing an action of SL2.
I see.
So I think that modularity comes up as the value of this theory on the 2 torus. And if you so for lens spaces, right, Skein modules of lens spaces, you might see a shadow of the automorphisms of a Heegart splitting of it.
I see.
So anyway, I'm just sharing my thoughts for how to.
I see.
I don't know if this is the right thing to say.
Okay. Can you prove this H0 is finite dimensional?
Oh, yeah, right. So my colleague here at Montana State is Sam Gunningham, and who was involved with the paper that no doubt you're aware of and referring to there.
Yeah. Okay.
And so this perspective on Skein modules, I don't think contributes logically. I think it's like orthogonal to finite dimensionality of Skein modules. But Sam seems convinced that the same theory that they used in their paper for finite dimensionality of Skein modules is so good that it also implies that actually this entire chain complex here is finite dimensional.
I see.
So Sam, we're enthusiastically talking about that project presently.
I see. Okay, thank you very much.
Yeah, thanks
Is
for your
this
question.
Q generic or root of unity?
Yeah, thanks for that question as well. And that definitely generic. Semi-simplicity is super important here for the the rigidity assumptions that are abound. There would be an interesting for tilting modules. I think that's also maybe I shouldn't say too much. Yes, Q is generic here for this statement.
And M is assumed to be closed.
Thanks. M is any compact manifold with boundary for this statement.
Oh, then probably SL2Z can act on, let's say, T2 cross I.
Yeah, right. Yeah.
Okay, thank you.
Let's see, I had another example, but I think given the time, I'm going to skip that. I would like to, I don't know, we're quite over time. My intention was to name some features of factorization homology that make it computable and easy to work with, as opposed to referencing the definition. And this is analogous, as some of you may know, in algebraic topology, between the Eilenberg-Steenrod axioms for homology. And with those, you can compute homology on just about everything. And you don't even have to need to know the definition of factorization homology to do those computations. So with my collaborators, we establish some features of factorization homology that essentially characterize it, similar to the Eilenberg-Steenrod axioms. So I think maybe what I'd like to do is, if there, and Liang, you can give me some input here, is to talk about those features and give an example of something that you can construct from just those features without knowing any of the values. Does that seem like a reasonable arc for the remainder of the talk? That might be 10 minutes.
Sorry, I mute myself. Don't worry too much about the time. If you prefer to talk about it, I mean, if anyone want to leave for lunch, that's okay. But I will stay as long as you want to talk. It doesn't matter.
I also wish to listen.
Yeah. Is it okay for you? Because
yes.
If you want to go home early, then we can stop. You can stop then.
That works for me. Okay.
Okay. Yeah.
Well, I will not be offended if people need to move on with their days.
Don't worry about it.
So, okay. So here's some features of factorization homology, and one is that the value on Euclidean spaces is something familiar. The value on RK is K endomorphisms of the special point. So in a sense, these values are the like codimension K topological operators.
So sorry, can you remind me about R again? R is an infinity n category, right? K is something smaller than n.
Yeah.
Okay.
So this is like it's for all K less than or equal to n.
Okay.
This is true. So so in other words, on R 0, that's the moduli space of objects of R. And on Rn, this is the n endomorphisms of R, or in R of the unit. And that was the EN algebra that we talked about earlier. So that's the codimension 0 or point observables are this are this EN algebra. So that's one, and this is a theorem, it's not a definition. And I'll mention some others that are pretty easy. So functoriality in R, that's probably not surprising to anybody. There's two kinds of functorialities in the manifold. And I'll give an example demonstrating the utility of both of these functorialities in a second. Given an open embedding, that determines a map between these values of factorization homology. And just to note, here is where the point in R is being used in particular. In a sense, if you have a disk stratification of M and an embedding of it into a larger one, you just extend by the unit everywhere. Another functoriality is that it's oppositely functorial in proper fiber bundles. So here's where we're really going to use that we're interested in values where this has dimension. Often this will have dimension equal to n, whereas this will have dimension strictly less than n. And that gives a map the other way. And this is kind of like degeneracies or identities. This is kind of like, this captures, in some sense, the anti-collision moves. And more functoriality in R is that factorization homology is continuous. So somehow this, I think, comes across as rather innocuous, this last bullet, and yet it just reflects on constructions of, for instance, Turaev-Vero invariants or Reshtikin-Turaev invariants, where one picks a triangulation of a manifold in order to define the invariant. And in doing so, it makes it essentially impossible to have a continuous action of the diffeomorphisms of M. So this is really an advantage of this approach, namely that one does not choose any triangulations or anything like that of M in order to define factorization homology. An advantage is that there's this manifest continuous action of diffeomorphisms. And this is something I'm quite curious about, is what this results in. Even if one is only interested in H0, one can produce elements in H0 from negative degree elements in this, essentially the Skein module, and positive degree elements in diffeomorphisms. So like when R is like 1, these like the one form symmetries that result from this continuous action here smear out negative one-dimensional elements in this chain complex to get zero-dimensional elements in the Skein module. And indeed, it's expected that factorization homology will often output negative chain complexes that have some, possibly have some homology in negative degrees. Just look at this expression, and typically endomorphisms of objects are concentrated in negative degrees. So I think this is interesting, and John nor I have really explored it at this point. A couple of you made some comments related to this. There's a type of Fubini theorem for factorization homology, that the value on a product over a product manifold can be figured out by first integrating over one of the factors, and that naturally is an n minus dimension of capital N category, which can then be input into factorization homology over this m-manifold. And so the right-hand side here indeed makes sense. And this is another theorem. It's not straight from the definitions. And of the theorems I've mentioned so far, these ones, this one is among the harder ones. And then there's a local to global principle. For those familiar with the alpha version of factorization homology, this might look familiar. It's excision. So if you're given a manifold and a splitting of it, that determines a computation of factorization homology over the ambient manifold as this expression. And whatever this expression means, I hope that you, just by looking at it, can appreciate that the left-hand side only depends on the value on these pieces of the manifold. So this is a way of computing the value on the whole manifold in terms of the pieces. And in order to make sense of this expression, I'll just kind of say it's a co-end indexed by this one category, because this common boundary here has codimension 1. And as so, this is a right module for it, and this is a left module for it. And then finally, there's the Morita invariants that I already mentioned. And with these features, one can work with factorization homology, only taking these as axioms and not having to know the definition. That's a paradigm that I believe is the case. I'll illustrate an application of this.
David, I have a question. So I forgot the setting for R again. It's a infinity n category, but you assume rigidity, you assume a monoidalness, right?
Thanks. So R, I didn't re-say it.
Because I want to understand what the meaning of Morita between
Okay,
R and R prime.
Yeah, so here R is a pointed, rigid, and I haven't fully said what rigid is, infinity n category, enriched over V, which let's just say is chain complexes over C.
Okay.
So there's no monoidal structure, but maybe the term rigid, I'll say what that means. Rigid.
That means all the morphisms are dualizable?
Are adjointable.
Adjointable, okay, yeah. Okay, yeah. So then what do you mean by Morita equivalence, I wonder?
Yeah, okay. Means, I'll just write this for those. So each K morphism has both a left and a right adjoint. And as I commented earlier, BA is rigid if and only if A is rigid, monoidal category. And that's as a 2 category. So that's why it's a generalization of that. That's why that term is used. I'll say what Morita invariance means. So definition, let R0, R1 be as above. So there are n categories, infinity n categories that are rigid, implemented. A R0, R1 bimodule is a V-enriched functor, V-linear functor, R0, 1 op, cross R1 to cat infinity n-1 of V, enriched in V. And these can be, so coend defines composition of such. So given a R0, R1 bimodule and an R1, R2 bimodule, you can take a coend over the intermediate R1 to get an R0, R2 bimodule. And we'll say that R0 and R1 are Morita equivalent. If there's an R0, R1 and an R1, R0 pair of bimodules to implement equivalences. Is that answering that question?
Sorry, I muted myself. So I think you answered my question, but I have another question. Is that this seems if R0, R1 is the delooping of a monoidal category, then it recovered the Euro notion of Morita equivalence, right?
Yep.
I see. Yeah, looks like
Yeah.
Thank you.
And one this is related to my earlier comment about perf and algebraic K theory. There's this interesting there's for one category is there's idempotent completion, and here's a thing that's true about. I'll state it for algebras, and just kind of let your imagination develop how it could be true for higher categories. So if A and B are algebras, a AB bimodule which is an AB bimodule is the same, so M is this exact same thing as a colorant preserving functor from A modules to B modules. So this is kind of a representability. It's rather tautological, but it's a representability of bimodules. So note that these are like E1 monoidal vector spaces. And these are one or even infinity one categories over vect, or that are enriched over vector spaces. So we can represent bimodules as functors between categories. This is kind of one motivation for considering categories, not algebras. And furthermore, it follows from this I'll just say therefore, A is Morita equivalent to B if and only if perf A is equivalent, not Morita equivalent, but equivalent to B. So this is kind of like the alpha story, and this is the beta story, which is somehow better. And there's a similar discussion in the higher categorical setting for what perf is and could be and stuff.
Thank you.
Yeah. Okay, so just using those features that I mentioned about factorization homology, one can construct the Jones polynomial. One doesn't have to know the definition of factorization homology. One can just use those features together with the computation I mentioned of Skein modules. So here's how that goes. Given a framed link in R3, so by that I mean it's a compact one-dimensional submanifold equipped with a trivialization, a null homotopy of its Gauss map. Then, given a framed link, one can construct this span of manifolds. So here's R3, here's R2 cross the link. And using the framing of the link, then there's an embedding of this little thickening, this R2 thickening of L into R3. Also, there's just a projection of R2 cross L onto R2. And I mentioned those peculiar functorialities in the manifold. One is opposite with respect to proper fiber bundles. This is one such. It's a fiber bundle and it's proper because L is compact. So one gets a map like this on factorization homology. And it's covariantly functorial with respect to open embeddings. So one gets a map like this. Therefore, a composite map. The value on R2, and gosh, I just saw I'm kind of messing up this was for rep B2 of rep QG. Finite dimensional. And so this is if you keep track, so the value on R2 were the two endomorphisms of the point, which was the moduli space of objects rep QG. So this is the moduli space of rep of finite dimensional modules for that quasi-triangular Hopf algebra. And similarly, the value on R3 are the one endomorphisms of the unit in rep QG, which in the case of SL when G is little SL2, and more generally even, the endomorphisms of the unit is rational functions. So this composite on factorization homology through these calculations on Euclidean spaces determines a way of assigning to every finite dimensional representation of little SL2 a rational function. And that agrees with the Jones polynomial. Specifically, when you evaluate on the fundamental representation, you literally get the Jones polynomial. So I hope this illustrates that how to use those features, at least to get something familiar, without having to know the definition of factorization homology. It also demonstrates the utility of both of these kinds of morphisms between manifolds. Other features is that there is now a excision formula for Skein modules. Which,
sorry, can I ask a questions?
Please.
These framed link it's not like in the rest-seeking-Turayev theory, you decorate the link by certain object in the representation. But in order to get the Jones polynomial, you somehow need to sum up all the possible labels, right?
Let's see. In order to get the Jones polynomial, I don't think you need to sum up all the labels. If I'm following
the Jones polynomial needs other colors.
That's right. Yeah.
The Jones only need the C2, the fundamental representation.
Only need this. I see.
Yep. That's right.
Okay, so this actually answered my question. I sent some days ago. I sent an email to you. I was wondering how to compute this. Yeah. So I think you simply answered that question by saying that okay, in order to do this, you cannot use the alpha version. You can do it in the beta version of the Factorization homology, right?
Right.
Basically, that's that.
Yeah.
Okay.
I actually
very good.
I got your email, by the way.
Oh, really? Okay.
I got an email about the seminar.
Yeah, I have an early email. Okay, I'll resend you. Okay.
Okay, thank you. Okay, and I'll just mention a couple of more things. So there, a student of David Jordan, I forget her first name, last name Cook, has some work on Skein modules that show essentially you have right exactness of Skein modules that suggest that excision should be true for Skein modules. And what was missing, of course, is a derived theory of Skein modules to account for, to fill in the rest of that right exactness to a long exact sequence. So I'm just going to leave it at that one gets from this a excision formula for Skein modules. And as I already mentioned, one gets a diffeomorphism action on Skein modules, which I think would be pretty interesting for constructing elements and for constructing skeins. Yeah, so I think I'm going to stop there. There's anyway, there's some other things that I had prepared that we could have another time in some discussion more informally with some of you. So thanks so much for your long attention of 2 hours. I really appreciate it. Yeah.
Okay.
Happy to answer some questions if there are any more.
Yeah. Thank you very much. Let's thank speaker for very exciting talks. Are there any questions?
So will you be able to use excision to compute the factorization homology for, let's say, a closed 3 manifolds as a result of link surgery?
Certainly. I mean, in principle, yes. To actually compute it, I think would be involved. Yeah, so for computing some of these values for lens spaces, it's something that I've considered a bit. And I think that's a place to start for that. But yeah, it gives an approach for sure, especially if one is truncating the values. Like if one is only wanting to know H0 of these values, then I think it would be fun to work out computations for lens spaces.
Okay.
So in particular, if you choose a modular tensor category, using this beta version of Factorization homology, you can recover all the rest-seeking Turayev TQFT, right? I mean the value of the resting TQFT on any three manifold with embedded coupon or links.
Yes, that's the
You
idea.
can definitely do that. Yeah.
Yes.
And from your theory, is that the tautological consequence?
Yeah.
Yeah. Okay. I see. Yeah.
So what's the difficulty construct this 40 TQFT you briefly mentioned that the
Yeah. Yeah. The
whose boundaries is really this restricting to life.
yeah. It's more like the difficulty is that it's just not the value on a four manifold will be a map between vector spaces. It won't.
Yep.
Whereas the value of by factorization homology on a four manifold will be like a chain complex or something. So it just doesn't fit. It's just not literally describable by a factorization homology. That's just a comment that like one needs to do something else. And there's an interesting so a lot of inspiration can be drawn by looking at much lower dimensions. So like for instance in dimension 1, so for 1 categories, one can look at a theory of factorization homology over 1 manifolds for 1 categories, and the output is chain complexes. Now with suitable finiteness conditions on a 1 category, specifically that it's Azumaya, namely that is dualizable both as a module for the unit and as a bimodule for itself. And that's an extremely strong finiteness condition. But if you have a monodal category that's Azumaya, then that then in particular it's dualizable over its center. And its center is a 2 category. So one can evaluate its center on 2 manifolds, in particular 2 manifolds with boundary. And there's a theorem, and this, so one can prove a theorem for 2-dimensional factorization homology that that the value on a surface with boundary with coefficients in the center is the same as the value of factorization homology on the boundary with coefficients in the original monodal category. And that calculation, which is a non-trivial calculation, determines a linear map. Given a 2-dimensional cobordism, it determines a linear map. So the difficulty, I alluded. So the difficulty is proving a version of that theorem I just mentioned, but for higher dimensions. Specifically, given a rigid infinity n category, one can consider its center, and that's a n+1 category. And so first challenge is understand in practical terms what it means for your arbitration for R to be dualizable over Z of R, its center. And then second challenge is to prove that similar theorem that factorization homology over a cobordism n+1 manifold with coefficients in Z of R is equivalent with the value on the incoming boundary dual tensored with the value on the outgoing boundary.
I see.
Anyway, I don't know practical conditions in higher dimensions.
I see.
For checking that Azumaya condition. Like essentially, I have no examples, and I suspect modular tensor categories provide such examples, but I don't know how to check that. And then And then again, that second challenge is how to prove that theorem I mentioned, which by the way is, in the case of a cobordism from the empty manifold to itself, is an instance of Morita invariance. So that more general theorem is some like a relative version of Morita invariance. And that would be an interesting thing to compute, like probably the most interesting thing to compute about the general theory of factorization homology. Thanks for that question.
I see. Thanks.
Any other questions?
So in your talk, I think you talk about closed and open manifolds like Rn or closed manifolds freely. Is there any technical difference between dealing with open and closed manifolds?
Yeah, that's a good and important question. So I think it's actually it's easiest to work entirely with compact stratified spaces. Okay, of dimension less 3 over the n. Now, given a non-compact manifold, one can compactify it to a manifold with corners or something like that.
Okay.
Now, that is not always possible if you have like some infinite genus surface type phenomena. So one can just restrict to suitably finitary non-compact manifolds, which are manifolds that admit compactifications to a compact manifold. That's the nicest place to work, I think, and that's actually where we. I don't know if that is addressing the kind of issues that you had in mind.
Yeah, I think that's fine. I was just wondering. So in your so you're proposing proposing a formal studying factorization homology in an axiomatic way or using their formal property, right? And you list the first property is the Euclidean property with Rn. Okay, right? But then you talk about closed manifolds with boundaries. So I was thinking about interaction.
So like one can really interpret that as dk rel with rel boundary. You know?
I see. Okay. Thank you.
But with boundaries, I probably didn't. Did you mention what if you have the boundary? What kind of a boundary condition you?
Right.
Would that be?
In a sense, that's what you label by the unit. So, so for a closed disk, one can choose a triangulation of it.
Yeah.
And then when looking at the labeling conditions, these can be arbitrary, alpha, beta, etc. But out here, it's always the unit on the boundary.
It seems that you can definitely generalize this, right?
Yes.
To include more.
Yep, some kind of relative, for sure. Yeah, I think that would be a fun thing to think through is the general defect type picture, right? Bulk or like bulk and boundary action.
Right.
Yeah, that would be interesting.
Yeah, thank you. Any other questions?
Excuse me. Is this factorization homology for the Skein module related to the Havandov homology?
Yeah, that's I like that question also. I'm not the expert to talk with about that. I'll say briefly what I do know. So Kovanov homology, maybe as you know, is expected to be a 4-dimensional theory. it's expected to be a four-dimensional theory characterized by its point, line, and surface operators, and nothing else. And so to match that with factorization homology, one would expect for there to be a braided monoidal 2 category. So the total categorical level adds up to 4 there, right? An E2 monoidal 2 category. And surely such a thing would be a categorification of the E2 monoidal 1 category of quantum representations. So in order to recover Copenhagen homology as an instance of factorization homology, I think that project is really a project of constructing a braided monoidal 2 category that categorifies rep QG. And that's not, so once that is constructed, then I suspect Copenhagen homology could be an instance of factorization homology. But constructing that categorification, I know some people are thinking about it very much. And the last I heard the status of that, it was, still just a shadow of that has been developed by, there's one community, Aaron Mazelji, one of my collaborators, Paul Bedrick, Katerina Stropel, and then another community comprised of Roquier and some others. So anyway, there's some people working that out, and I don't have too much to say about what that categorification of rep QG would look like exactly.
I think Noda has a paper on categorifying the quantum SL2. Probably that's related, fit into your picture, I mean.
Yeah, for sure. I guess I am, that's right. I can't remember what the status of that is, namely if there is a braided monoidal 2 category of such, or if there's just a description of what the objects in there are. You know what I mean?
Yes. Thank you very much for the great comments. Thanks.
All right. Any other questions? It looks like we have too many questions today. Thank you. Be patient with our questions. Any other questions? I think it's a great opportunity to ask questions about factorization homology to the co-founders of the subject, right? Any other questions? Actually, I have a lot of questions. I sent an email to you some times ago, but perhaps you didn't receive it. I'll do that later. Maybe I'll send you another one. Yeah. Maybe I'll organize my questions in my emails. But because I have too many questions, I don't know where to start. Any other questions? Yeah.
Actually, I invite a video call together. That might, I mean, it depends, but that could be more efficient than email exchanges. So I'll leave that up to you. But yeah.
Oh, okay. Okay. Any other questions from the audience?
Is this recording available at some URL?
Oh, yeah, that's a good point.
We will make it available. I think we have a YouTube channel, so I will announce it in the group, and I'll let Yang announce it in other groups.
I see.
Oh, okay.
Yeah.
Okay.
That'll be
Thank you very much.
fantastic. Yeah. Okay. If there's no further questions, let's thank speaker again for this wonderful talks.
Thank you very much.
I really learned a lot from you. So thank you very much.